Hello, it's David. Now today's video is slightly different from my normal retro computer fare, but I hope it is a little bit of an interesting look into the world of developing electronics projects. As you may know, I haven't had a lot of time to work on projects of late, so I thought I'd do a quick side project to fulfill a requirement that I have, and it turned into an absolute marathon. I've cut down as much as I can from these videos, but it's still going to be at least a two-parter, maybe even a three, and I haven't even shown you some of the prototypes that I made along the way. So I do hope you find this at least a little bit interesting, perhaps a little bit enjoyable, and let's go and learn some electronics together. This is a great big lithium-ion battery pack from my electric motor scooter. It looks like this. That's up for sale at the moment and it hasn't had much interest, so currently it's stored in my garage. But the battery packs here I don't want to leave in a state where they are either fully discharged or fully charged, and basically are deteriorating just through storage. So what I thought is I could maybe build a little circuit that will cycle these and try and estimate the battery pack percentage and sort of keep them regulated to a reasonable level. So I was thinking I could get one of these specialist power monitor chips, knock up a quick circuit board with PCBWay, and see if we can monitor a charge-discharge cycle with these things. Okay, so this is the circuit that I've come up with. The battery is attached basically top and bottom of here, so this is the positive input, the negative input. I should say that these are 70 volt. I think actually it's probably maybe 60, but I think the peak, well, it's specified as 60, but I think the peak load is about 72 volts. So we're talking the 70 volt range. So battery's connected to here, and basically what we have is two relays. This first relay is effectively the master enable disable, and we have a heavy trace going down to a second relay here, which will choose to either send the load via this is the load on this side, we'll send it via a load, or it can cut in a charger instead, which is attached via these two jumper points here, which will in effect reverse the polarity of this circuit and back charge the battery. So we can basically have it go through a complete charge discharge cycle to get a calibration, and then we can top up and drain, top up and drain to maybe sort of like, I don't know what, between 40 and 60% or something like that, just to keep the battery in decent state of charge and good health. So these two relays will be controlled over here by a couple of P-channel MOSFETs, which are held high when not being driven, and these will be attached to signals coming from what I propose to use is a Raspberry Pi Zero. So I've got a Raspberry Pi header on here, and what we'll do is we'll basically either pull, the reason I'm doing it like this is because this is a 5 volt relay and Raspberry Pi is 3.3, so what we'll do is we'll either pull the relay one line, which is just on one of the GPIO pins, got it on GPIO 17 and 18 for 1 and 2. So we'll pull it low, or we'll allow it to go high impedance. So we'll switch to input basically, and that'll be pulled up, which would turn off the P-channel MOSFET. That switches relay 1, same setup to switch relay 2, and across the coil terminals on the relays, we've got a reverse polarity diode, so that we don't shunt any of that magnetic basically magnetically converted electricity back into the Raspberry Pi and blow it up when the relays disengage. So these two sense points here will go off to a specialist power measurement chip. So we're going to be using the INA237. This is capable of, I think, up to 80 volts if memory serves. So it should be fine for this arrangement, which is in the 60 to 70 volt region. And this is controlled via, I can't remember if it's I2C or whether it's SPI, SDA and SCL. Which one's that? Yeah, there's no pin select there, so it must be, yeah, address monitor. Yeah, this is I2C. So this will connect to the Raspberry Pi. Again, we just attach the I2C lines up to the normal I2C connections on the Pi. So this sets the Pi via I2C. We just hold our to address select to ground, so that gives it a particular I2C address. You can have more than one chip if you program those differently. And the sense lines will come in here, and there's a little bit of a resistor capacitor sort of filtering arrangement there, only 10 ohms and 100 nan. That gives us then an idea of the current flowing through the shunt resistor. Also, the Sense Plus pin is also connected here to the bus voltage measurement, so it'll measure the voltage independently of the current flow, and it will actually infer power for us directly. I've made provision for some additional I2C ports over here, and some push button configuration switches here, which will sort of pull Pi, potentially a rotary encoder, which can all be wired through to the Pi. So perhaps we can basically have like a two-line dot matrix display and some push button input or something like that if I want to get advanced. Otherwise it would just be all done through an SSH terminal session.
I'd like to thank this video's sponsor and the supplier of my project PCBs, PCBWay. PCBWay aren't just about PCBs either, although they are extremely good at that. They also offer component assembly, CNC machining, 3D printing, and a variety of other manufacturing services. They have a number of community-focused offerings too. The Shared Project Hub is an open platform for makers to share and exchange their ideas, and the PCBWay store is a great place to pick up assembled modules. I mean, who wouldn't want a musical Tesla coil? So many thanks again to PCBWay, and I recommend you have a look at some of the links included down below.
Now PCBWay have done their magic, and this is the board I've received back. Red because it's high voltage, 60 volts. Anyway, there's the Raspberry Pi pin header that will go on the reverse of the board there. There's our two relays there. We've got space there. I should have put them on the back. That's silly. We've got space there for our rotary encoder. 3 switches. Basically, it's a choice of rotary encoder or these two. So it's switch 1, 2, 3, or switch 1 and the rotary encoder, because they use the same lines. Our power measurement chip will sit over here. IC1. Look how tiny it is. A couple of resistor networks. A couple of biasing resistors. There's our filtering section there. Diodes over here, just tiny little 0805 diodes to help drain that back current. And here are our inputs. So we've got our Sense Plus and Sense Minus, which are little thin lines here. We've got our big negative shunt side input. That's a power input, runs through the first relay, and then it either connects to the charger plus or the load plus. And then we've got a common set of charge minus, load minus, and battery minus connections on the bottom there. I'm going to be using this old Raspberry Pi Zero here, which I blocked the Wi-Fi on a little while back, so it's got a Wi-Fi dongle hanging out the side. But if I end up frying this with my enormous battery pack, it's not the end of the world because it's half dead anyway. So that's the plan for that. And I've had a go at designing 3D printing a little tray, basically the bottom half of a case, that I could perhaps enclose this in. It's only a prototype, hasn't really worked very well. I've printed that one far too close to the ground, and I've got a lovely bit of blue masking tape onto that, and you can see this corner's lifted, but hopefully that'll be good enough for a little bit of experimentation anyway. Okay, so I think we'll get started with the hardest components first, the most fiddly ones. There is my INA 237 chip, tiny little thing, got to get onto that footprint there. So same way I do all my SMD work, by hand, using a K-tip on the soldering iron at 290 degrees. A bit of flux on both sides. We'll try to align it by hand initially. Let me zoom you in there. Yeah, we'll try and align this by hand initially, and see if we can tack the corner down. So I'm seeing a little dot down in that corner. It's very difficult to discern down in, as you're looking at it, the bottom left corner. So that lines up with the long line on my silk screen here. So I think we'll just try and get that roughly into position. I haven't got my solder ready, I'm going to have to do that twice. Just a small blob of solder on the tip of the iron there. Right, let's try and do that again. Right, we'll line that up. The pads are nice and long here, so actually there's quite a lot of room to work. There we go, we'll just tag that side down, press the chip down flat, and I've absolutely flooded that side with solder, but never mind, that shall hold it. I'll just inspect the alignment. Yep, I think that looks, because it's all flooded at the bottom, but you can see the alignment's okay, I think, on the other side. So I'll just come in now and solder those other pins. Tiniest little bit of solder on my tip. Once again, I'll hold it down just to stop any floating pins. A little bit of a drag. First between pad and pin, and then running down the line of the pins themselves. I think that side is absolutely fine. So in order to get rid of the excess solder on the other side, we'll wipe the iron clean, and then it'll be a case of just repeating the process and see if we can pick up some of the get into shot. There we go. See if we can pick up some of that excess solder onto the iron itself. I'm actually contaminating some other pads here. And if that's not sufficient, then we will simply, oh dear, what's that muck on there? We'll simply bring in a little bit of braid and redo it from scratch. I think I've introduced some muck onto the board. Bit burnt flux, I think. And there we go, I think we're all soldered up okay there. There's a little bit of that black grime between those two pins. I might have to try and clean that a bit more because I don't know whether that's conductive. And you can see actually two pads, one on C1 there to your left, and one on C2 there to the bottom of the screen. I've accidentally infected with a little bit of solder. To be honest, I could simply just put the capacitors on, reflow that, no trouble at all. But I can also just clean it up, depending on my preference. And in this case, I'm just going to clean it up. Okay, so there we go. That's the majority of the SMT parts. In fact, all of the SMT parts, I think, sorted out. So now it's time for the big ticket through-hole items, the boring ones. We've got two relays, we've got the 40-pin header socket, and there's a couple of BS 250 MOSFETs to go in here. So we'll get those put in, and then it's time for us to actually have a go with the software. Okay, well, these MOSFETs that I have here are of slightly dubious provenance. I got them off eBay because to order just such a small number from Mouse or somewhere like that is just not worth it. So first things first, I'm going to trim the legs off because they were stuck in goo. And then just to verify what I have here, I've got this cheap Chinese component tester. So let's strap it in and see what it comes up with. So this says we've got ourselves a P MOSFET. That's good. Can you, I don't know, can you quite make that out there? There we go. We've got a P MOSFET, and it looks like the drain is pin 1. He says, trying to get that into shot. There we go. Drain's pin 1, gate 2, source 3. Okay, I think we're going to have to buzz that out. pin 1 should, as I understand it, be the 5-volt rail. Yep, so I think my silk screen is rubbish. Important to bear in mind. That is probably the minimum needed to be able to plug it in and do some testing. So, well, that's next. Okay, so here we are. We've got this a little bit cleaned up. It's still a little bit mucky, and I've got my sacrificial Raspberry Pi Zero here with its external Wi-Fi on account of me having blown it up previously. What I'm going to do is just squirt a little bit of contact cleaner into this header that I've put on here, because I never trust them. They always are a bit rubbish. Ooh, which one's pin 1? There we go. Pin 1 is down here in this corner. On the Pi, the square solder pad is pin 1, so that means it must be that way around. Yep, that makes sense. We'll slot that in there. No, we won't. That's off by 1. Had to blow up your Pi again. There we go. Let's just see if we can talk to the chip for now. So let's power this up. We'll try and log into it, and we'll get the data sheet out for the INA. I think it's INA 237 I've got on there. So first things first, does anything go bang? Get the power code the right way around. Oh, nothing went bang, but I heard my relays click. I don't know if you picked that one up. So there's power there. And we've got ourselves a green flishy flashy light. Okay, I think let's get the laptop out and see what we can see. Okay, here we are. I've managed to log into our Raspberry Pi, which is just off camera here. And I've made some notes up here as to what I need to do to identify my chip. So the INA 237, I've got my data sheet up here. It's an I2C chip, and I have both the address registers, which are configurable here, tied to ground. So I think, well, to be honest, we'll just run the I2C detect command, because that should I2C detect, there we go, because that should be able to probe the bus. I shouldn't need to have to calculate what it is. So I2C bus, I think it's bus 1. This can confuse your I2C bus, cause data, blah, 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 blah. Will it continue? Yes. There we go. We've got one chip identified, one I2C target identified at position 40. So, okay, so let's do I2C get. We'll try and ask for something. -y skips that interactive. I don't need to worry about that. So bus 1, address 40, Wi-Fi is dropping out, and then we send a command, and that's what this section of the manual tells us. So I'm just going to try and read the bus voltage. So that says 5 hex. So the command is 5. It's a type of read. And it's bit 0 to 15, so that makes it a word length read. So so I say command 5. Okay, so command 5 and a word read. Warning: this program can confuse your eyes. Blah 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 blah. I'm going to read there. Yeah. Do it. Yep. And we've got a hex value of 100. So dropping into our programmer's calculator, 100 is a decimal 256. Obviously it's one up from FF, which is 255. Right, so what does 256 mean? So a conversion factor, so it's a 2's complement value, however always positive. The conversion factor, well, what's the point of it being a 2 complement? That means there's a bit wasted, doesn't it? Anyway. Conversion factor is 3.125 millivolts per least significant bit. Right, so what did we have? We had 256 and we times 3.125 millivolts, 800 millivolts, which is 0.8 volts. So, I mean, basically it should be reading nothing. because there's nothing attached. So I mean, that must be floating. So what we should probably do is to wire it up to a voltage source, and we'll give it a test. Trying to think what the best way to do this is without blowing anything up. Hold that thought. Okay, so hopefully you can still read what's on the screen here, but what I've done is basically set this up in a bash script loop to the -y, by the way, just means it won't ask for interactive, so it's doing the same thing, asking for a word from port 5 just every second, basically. So it's asking for it, sleeping a second, asking for it again, and if I run that now, it's actually slightly off camera, there we go, it's actually gone to 0. Okay, well that's good, that's what I was expecting the first time. So maybe we just, oh no, there we go, it's jumped up to so okay, I suspect it's because the input's floating. So what I've done is I've got my crappy little Chinese power supply here, eBay style power supply, and I've set it for 1 volt with a maximum current of 100 milliamps, and I've got the negative clipped onto the B- here on my board, and what I'm going to do is attach the positive croc clip to the Sense Plus line. And the reason I'm attaching it to the Sense Plus line is because if we return to my schematic here, we're trying to read the bus voltage, V bus, on the 237, and that is a direct connection to Sense Plus. Sense Plus doesn't go anywhere. Sense Plus only goes to basically the chip. So Sense Plus goes to the chip via that filter mechanism, and also to the chip via to the V bus pin. And obviously it's intended as a shunt resistor in there. There's no shunt resistor because I supply that outside the board. So there should be no current drawn. So this should just give us a voltage reading of whatever is going in on this croc clip. So let's just try clipping that on there now. There we go, and there we go. We've jumped up to 4001. Oh, 3F01 4001. Okay, so that's jumping around a little bit there. Let's just bring in my multimeter here, because I don't trust that power supply to actually supply what it says. Just get that slightly into shot there, and let's have a measure what's actually coming onto the board. Can I do this without blocking the screen? Actually, that's pretty good. 0.999100. That's pretty much bang on 1 volt. So that's actually pretty impressive. I suppose it's not under load. So we're getting 1 volt. So 4001 hex. If we come back to our calculator here, so 4001 hex is equal to, 4001 hex is equal to 16385. That's basically halfway, isn't it? If that's a 15-bit number, because it's 16-bit, but it said that it was always positive, which means that it's effectively 15-bit because it's never using the negative, the 2's complement bit. That's almost exactly halfway. 16384 is halfway, isn't it? 4000, 4000. I mean, so I don't know. I'm not sure if this makes sense. That doesn't make much sense to me. Let's just try that. So 16385 times, it was 3.125 millivolts. There we go. So that's apparently 51 volts. No, it's not. No. So okay. I think I might need to read the manual a little bit more, but we are communicating with the chip, and we are seeing that it is it's doing things. Right, I couldn't find I was doing anything wrong, to be honest, and then I had a bit of a head slap moment, which is something that I probably ought to have considered. Well, I haven't considered it because I'm using modern hardware, but when normally I work with Ataris and Amigas and 68000s where this sort of stuff is important. I'm talking about byte order. My suspicion is that this chip is sending results in big endian byte order. This is a word size result. So we're reading 4001 because this is an Intel based Mac I've got here, and this is a little endian system. So we're getting 15 bits back, 16 bits back. which this is interpreting as 4001 down here. We're still seeing 4001, but I think that's actually 0140. So, which to me makes more sense. So let's pop that in. Let's say that's 0140, which, oh, that's in hex. 0140, which in decimal is 320. That's starting to feel a bit more sensible now. 320 times 3.125 millivolts per bit. 1000 millivolts. 1 volt. Absolutely bang on. Ah, it's just a byte order issue. I was not expecting to see that on modern hardware. Would you believe it? Right, so, well, what happens then if we crank that up? I'm going to dial in a higher voltage here. Let's, shall we push the boat out and go up to 5 volts? This is capable, this is supposed to be capable of measuring up to 84, I think, it said in the data sheet, volts. So this really shouldn't break it. Right, so we've got 4994 on the multimeter. We're now returning 3D06, which I think is 063D. 1597, and we switch that over into the scientific calculator, and 3.125 millivolts per bit is 4.99 volts. 4.991 there, we've got 4.994. That's not bad. Our chip's working. Okay. Right, so I need to go away and learn how to script this properly. Get this, I suspect Python is the way to go. I should get this into some form of script, and we need to then figure out how we're actually going to wire up our board. Now, I have one of these great big current shunts. It's kind of got wires coming all off it from prototypes at the moment, so I'm not sure I can get it in camera. One of these enormous, great big current shunts here from an inline, basically from an automotive ammeter. That this could very well be far too powerful for, basically the precision would be far too low for what we're doing. I have these two power resistors here, but these I suspect are much too high resistance. This one is 2.2 ohms and this one is 12 ohms. And they're 25 watts, so they probably wouldn't dissipate enough of the heat. I think this is likely to be sort of in the milliohms region. This is in the ohms region. We probably need something in the fractions, like 1/10 of an ohm, really. So I'm not sure what we can use for the shunt, but maybe we'll experiment and see how we get on. But first and foremost, we need to get ourselves a script running, interpreting these big endian issues, so we can actually start doing some measurements.